Hello guys, my name is Ziad and today I wanted to show you something. You might be looking at these graphs right now and you might look at them in disgust. Because the fact is that most teenagers nowadays don't really like math. They view math as just this boring thing that they don't really care about, right? Well, I'm here to show you the beauty on these graphs and how these graphs actually relate to stuff that you actually care about, like video games for example. So there's this video game called Hollow Knight. It's a very famous video game and it's a really good video game as well that I play. Anyways, those graphs that you just saw here connect directly to this game in ways that you would never probably see. You see, and I already showed it to you actually here, but you just don't notice it because you don't understand these graphs nor do you see its connection to this. Now, how is it applied here? Well, it's in the camera movement. How I'm moving in this game and how it's so smooth and how it catches up to the player. If I use this ability for example and stop here, and how the camera follows the player then eases into stop, that's directly modeled using those graphs. Okay, now before you get scared, this is actually how it works. I wanna now show you how it works so you can understand it and appreciate its beauty. It works using this formula, and this formula is literally just these graphs, and this is how fast like the camera eases in. In the beginning, it's basically directly following the player, but then it starts slowing to the position of the player, and this is literally just this. So how exactly does this work? Let's have this animation to show us here. Let's say that this is the camera and this is the player. The player suddenly moves very far, as shown here, like I just showed you in that example. Player moved very far from the camera. The camera is its own object and the player is its own object, because you can't just make the player, just the camera follow the player statically, like the camera is just on the player, but that would be very just not smooth and would not look and feel good to play. This is why video game developers spend so much time doing stuff that you wouldn't really see in the game. They spend so much time just adding the smoothness factor of the game. So let's say that this is the player, this is the camera. Now using this formula, which I'm gonna explain in a little bit after this directly, you can just make the camera ease into the player like this. It moves closer and closer and closer, and then it moves in the beginning very quickly but then slows down near the player. Let's get the first frame. So how does this actually work? Well, let's say that this distance from the player to the camera is 100 units, right? Using this formula, we can basically describe what happens here. The first distance is 100, but then it moves half the distance, right? And now it's 50. It moves half the distance again. It's now 25, and again 12.5, and then again 6.25, and further on till you can just basically round it in the end. In the end, when the values just get super small, you can just basically make it rounded to the player position, because these values are going to be so small that they're basically negligible, and if that doesn't happen, then you could basically just say that this camera will just keep moving forever, infinitely. Anyways, this is basically it, and it works and it's very smooth because in the beginning, of course, 100 divided by 2 is 50, so you lost 50 units. It moved 50 units at once, but in this time it moved 25 units. In this time it moved 12.5 units. It's moving in increasingly smaller units until it reaches you, the player. And this is how this formula is made. A1 is the first unit of the turn of this sequence, which in this case it would be 100, because 100 is the distance. So you can say that A1 here is the distance, right? And then R is the ratio that we're multiplying this by. So here it's 0.5 because every time we multiply this 100 by 0.5, which is the same as dividing it by 2. But then we can actually change this ratio to change how quickly or slowly it is done. Like here, I made the R, I wrote it here, 0.75. So now, you think it's gonna get quicker or slower? It's going to get slower because we're multiplying by a bigger number, so the numbers are gonna get slower at a smaller rate. So like, to explain better here, this is the first bit. We still have the same 100 distance, just act like this distance is exactly 100. The second distance would be 75, which here it's 50. And then this third distance is going to be 50, and now this one is 25. So you see how it is? It's going to be way slower. As you can even see, this one has 18 frames until it touches the player, and this one only has 9. So if you play this animation here, you can see it moves way slower. You can see how slow it gets in the end. Now, of course, this is not a realistic case in a video game because I don't think video games really want to do that. But you know, they could still. There's probably find cases for this. But yeah, this one moves way slower, and then this one moves way quicker, almost exactly double as quick. So you can see how quickly this moves, and then how slower this one moves. And then if we decreased this ratio, which is saying again here the R, we can make it move way faster. Like, it's basically, this one is 5 frames compared to 18 frames here and 9 frames here. So the first distance is the 100 again. I'm using a fixed distance of 100 for all of them. The second distance is gonna be 0.25, or no, 25 actually, which is compared to here, this is 50, and then here is 75. This is 25. It moves way quicker. So if we play this here, it's way quicker than this, for example. This is like, this now feels so slow compared to this, and this is just the in between. So yeah, and this, now you can see this, you can see how this connects here exactly. This is the formula applied in Desmos, which is a very cool website. A1, which is the first unit as well, which you can just say is the first distance, is 100 in all of them. Let's just take one graph at a time. This is the graph that we have. That this graph basically describes this animation. 100 is the fixed distance, and then the ratio is 0.5 because we keep multiplying by 0.5 for every frame. And then we just make it to the power of x minus 1 to get us this graph, to the power of x minus 1. This is just fixed. And yeah, that's how we get it. This is how we see. And we can see here that, as I said before, we're moving huge distances in the beginning, but then as we get slower, we converge to the player's position. The x-intercept, or this line here, as we get closer to the line, this x line on the x-axis is basically the player. Here we're moving like huge distances, basically like going straight down to it, but then here we get slower and slower and slower. And so the 0.25 is actually going to reach here quicker because, as we said, it's gonna move way more distance. So here it reaches this quicker, but then the 0.75 one is gonna reach it later. And now, if we go to the game, we can now appreciate how they model this. They choose very specific values, and of course, they do in a way more complex way to make it even better, and they probably use different values for different situations, but we can still get the main idea of how the player moves in such a smooth way and how the camera comes to a halt in such a smooth way. So now we can understand all of this, and now we understand how geometric sequences work, because this is called the geometric sequence if you don't already know. So I hope you enjoyed, and I hope you learned something, and see you in the next video. We're gonna cover another very interesting video.